Hello everyone, this is Amika Mahajan. Welcome to my channel. This video is focused on magnetic effect of current. In this video, I'm going to discuss one NCERT problem in which there is a long straight wire of cross-section A. Is the radius of that cross-section which is carrying current I. The current I is uniformly distributed across this cross-section. We have to calculate magnetic field in the region R greater than this A and R less than this A. So first of all, I will consider the case when point is lying outside the wire. The point is P. So distance of point P from the center is R, which is greater than radius of cross section of the wire. So I consider a closed loop passing through this point and divide whole loop in small segments, infinite small segments, each of length dl, and I consider one such segment AB. Now, magnetic flux density B and segment dl both are in same direction. So, B dot dl will be B dl cos 0 degree. And if I have to consider whole loop, then I have to integrate over the closed loop from 0 to 2 pi r. 2 pi r will be length of this loop, which is equal to circumference. So B dot dl integration over the closed loop from 0 to 2 pi r will be B dl cos 0 degree. And when I put limits after integrating, B will be constant. So integration of 1 with respect to dl, it will be L. So in place of L, first I will put upper limit 2 pi r. It will be B into 2 pi r minus lower limit 0. So left hand side will be B into 2 pi r. This one. And according to Ampere's second law, this should be equal to mu naught times total current threading the loop. Here, total current threading this loop will be I. So B can be calculated. B will be mu naught I by 2 pi r. So what we find? Field outside the wire will be inversely proportional to distance of point P from the center of the wire. Now I will consider another case for R less than A. This was for R greater than A. Suppose this is the loop 1, and it is again concentric circle with the cross section. Now I divide this whole loop in small segments, each of length dl, and consider one such segment. Again, this segment dl length and flux density B, they are in same direction. So if I take B dot dl, it will be B dl cos 0 degree equal to B dl. If I have to consider whole loop, then I have to integrate. So B dot dl over the closed loop. Now what will be the limits again? 0 to 2 pi r, but r is less than a because this point P is lying inside the wire, less than radius a. So B dl cos 0 degree, and again B is constant, integration of 1 with respect to L. So it will be L by putting limits, first upper limit 2 pi r, then lower limit 0. So I get B into 2 pi r on left hand side, same as in previous case. But in this case, I is total current, which is uniformly distributed over wire. Now I have to consider current threading through this loop. Let it is I dash. How I can calculate I dash? For area, whole area of radius A, it will be pi a square. Current flowing through wire was I, which was uniformly distributed throughout the wire. But for one area of cross section, it will be I by pi a square. And I have to calculate current through this cross section having radius r. So pi r square will be area of cross section of this segment. So for this, the current threading will be I by pi a square into pi r square. This pi will cancel. So I dash will be I r square upon a square. So I will put value in place of I dash. So what I get? B into 2 pi r mu naught I into r square upon a square. So when I take B, 2 pi r will go in denominator, 1 r will cancel and I will get mu naught I into r divided by 2 pi a square. Now in this region, B is directly proportional to r. For r less than a. And for r greater than a, it was inversely proportional to r. If this r is equal to a, if I consider point on the wire, then in place of r, I will put a. So in that case, b will be mu naught I into a upon 2 pi a square. 1a will cancel. It will be mu naught I by 2 pi a. This is for region r equal to a on the surface of the wire. So if I have to represent it graphically, variation of field with r, I will divide this in 3 regions. One inside r less than a, another r greater than a, and one on the surface. This is r equal to a. So what I find? For a region r less than a, b is directly proportional to r. So graph will be a straight line up to this region. Then for region r greater than a, it is inversely proportional to r. So exponent decrease in magnetic field for the region r greater than a. And maximum field will be on the surface at this point when r equal to a. So this is the graphical representation of field with distance of point r, whether it is lying outside the wire, on the wire, or inside the wire. So thanks for watching this video. Like, share, subscribe my channel.